Hi everyone. So today we're going to be talking about the complex number system. Actually, it's really just an introduction to it. But let's just talk about this is kind of one of the last units we're going to be working on, and or sections that we're going to be working on in this unit. And it's somewhat related to radicals. So let's remember there was a couple of situations where we got this under our radical, and I said for now, you don't want to get a number like that because that meant it was non-real. Because there's no real number that when we square is going to give us -9. And remember that the square root is the opposite of a square function. Um, but what we could do is maybe think of it like this: root 9 times root -1. And we know that root 9 is the number 3. Well, this square root of -1, we had to come up with a way for dealing with it. And it's actually something that we call a complex number or an imaginary number. So the square root of -1 is actually is what we're going to call it is I. So I is the same thing as negative square root of 1. All right, complex numbers are going to have I in them, and so they have two parts to them. The A part of a complex number is the real part, and the BI part is what we call the imaginary part. All right, so now let's talk about that. If we know that I is equal to the square root of -1, what would I squared be equal to? Okay, well, I squared then, if we squared both sides, would give me, it's kind of funny, it actually gives me -1. Because remember, the square just gets rid of the square root. So for our intensive purposes, we need to know that I squared is equal to -1. That's very important. And actually, the first four units or squares, or the first four exponents of I actually repeat. So we're going to let I equal itself, so I. And then I squared is -1, I cubed is -I, and I to the fourth is the number 1. And after that, it just starts to repeat. All right, well, how can we deal with then i's if I ask you for what's I to the 25th? We can use the concept of remainders, okay? If something goes into itself evenly, it would have no remainder. And so since it repeats every 4, that means we can divide the number by 4 and see what the remainder leaves us, okay? So if we get a remainder 1, the answer will be I. If we get a remainder 2, the answer will be -1. If we get a remainder 3, the answer will be -I. And if we get a remainder 4, it will be 1. I mean remainder 0, sorry. Remainder 0 would be 1 because 4 goes into it evenly. So what do I mean by that? Okay, so I to the 25. I divide 25 by 4. 4 goes into 25 6 times, which doesn't really matter we really only care about the remainder. But 4 times 6 is 24, which gives me a remainder of 1. So I to the 25th would be just I. All right, let's try the next one. I to the 39th. 39 divided by 4. 4 goes into 39 9 times, which is 36. And I get a remainder, what I'm left over with is a 3. So remainder 3, it would be -I. All right, I to the -6. We divide 6 by 4, we get a remainder of 2. Remainder 2 would be -1. Okay? All right, so that's one way we can deal with it. We can also look at numbers now that have that negative square root in them. So remember that we could always rewrite this as the square root of 25 times the square root of -1. Well, we know that the square root of 25 is 5, and we know that the square root of -1 is I, so our answer would be 5I. All right, let's try the second example. -9, I'm gonna write that as the square root of 9 times the square root of -1 minus 2 times, we already know that -25 is 5I. Okay, so this would become 3I minus 2 times 5 is 10I And then we can treat I like a variable, and we can combine like terms. So we get negative 7I. All right, keep going. Now, you don't have to write it as negative 1 every time. If you see the negative, you can just pull out an I. So here I would pull out an I, and root 3 does not simplify, so I leave it in the roots. Here I see the negative, so I pull out an I, and I'm left with the root of 6. But now I need to multiply. And so we multiply the outer parts and the inner parts. So I times I would give me I squared. Root 3 times root 6 would give me root 18. All right, but now I'm not done. I have to simplify. Root 18 can be rewritten as root 9 times root 2, which is 3 root 2. I squared, you know, is negative 1. So we're going to plug in negative 1, so we get negative 1 times 3 root 2. Now it's times, so we can multiply these outer parts, and we would get negative 3 root 2. All right, so hopefully it's starting to make a little bit of sense. Okay, so let's move on. Once we add an imaginary unit to a real number, we get a complex number. And remember I said that the A was the real part, the BI was the imaginary part. Okay, you can also add or multiply two complex numbers simply by treating I as if it were a variable and using the distributive property. So example 1, we have 2 plus 3I plus 4 plus 5I. The parentheses don't really matter, so I can actually remove them because it's addition. They matter if it is subtraction. All right, so now I'm going to combine the real parts, which are the 2 and the 4, giving me 6. And I'm going to combine the imaginary parts because they're like a variable, like terms. So 3I plus 5I, which gives me 8I. Again, the 6 is the real part, the 8I is the imaginary part. All right, so now with subtraction, we got to be a little bit careful. We have to make sure we distribute the negative first. So we get 5 minus 2I minus 6 minus 3I. All right, so now we combine the real terms and the imaginary terms. So 5 and negative 6, if I combine that, it's going to give me negative 1. And then negative 2I and negative 3I is going to give me negative 5I. And they're in simplest form. Okay, so now what about multiplication? So multiplication, if we're multiplying, we either distribute or we FOIL or we keep distributing. So here we have two binomials. So I know that binomials, when I multiply them, I can distribute. So I'm going to do 3 times 3, which is 9. That's my F. Outer terms, so 3 times negative I, so negative 3I. I times 3, which is plus 3I. And then I times I, which is going to give me negative I squared. Okay, so now you may notice that these, if you combine the like terms, they cancel. So you get 9 minus I squared. Okay, that's actually the difference of squares if you notice it, and so was that in factored form. But now we have to use that we know I squared is equal to negative 1, and we're gonna plug it in for I squared. So 9 minus negative 1. Anytime you see an I squared in an expression, you're going to plug in negative 1, no matter what. All right, so I plugged in a negative 1. I was careful to put it in parentheses because I know that I have to square it, right? And I have a negative on the outside, and I don't want to think that they don't relate to each other. So now I'm going to do negative times negative. So it becomes 9 plus 1, which gives me the real number 10. So you may notice that the imaginary part went away. All right, let's try the next one. Now that won't always happen, but it will happen if the binomials are the difference of squares pattern. All right, let's try this one. Root 2 plus I times root 2 minus I. So we do root 2 times root 2, which is 2, because it's root 4, and root 4 is 2. Root 2 times negative I is going to give me negative I root 2. I times root 2 is going to give me positive I root 2. And then I times negative I is going to give me negative I squared. All right, so now these guys are going to cancel, and we're going to get 2 minus I squared. All right, so 2 minus I squared. Now, I see the I squared which we know is -1, so I'm going to plug it in. And then I'm going to do 2 plus 1, which gives me the number 3. All right. So what's important here, guys, is that in examples 3 and 4, the factors, 3 plus I and 3 minus I and 2 plus I, 2 minus I, they are the same binomial. They're the same binomial with different signs. It's actually the difference of two squares pattern. Okay? And these are called complex conjugates. They're complex conjugates. The product, what you may have noticed and what I said, the product, which means multiplication of, the product of complex conjugates is always going to be a real number. All right, so why do we need this, Coach Fred? I don't understand. Okay, so let's look at our first example of why we need this. You may remember that I said, so we're looking at 1 all over 4 minus 3i. You may remember that I said we could never have a radical in the denominator, okay, like 1 over root 2, and we had to rationalize it by multiplying by root 2 over root 2 to make the bottom a real number, and so we would get root 2 over 2. Well, the same thing holds with I, because I is really like a radical, isn't it? It's the square root of -1. So in order to get rid of I, we have to multiply by the complex conjugate. So the complex conjugate of 4 plus 3i is just going to be 4 minus 3i is just going to be 4 plus 3i. So we multiply both the top and the bottom by the complex conjugate. And typically it'll say express it in a plus bi form, and that's what tells me I need to rationalize it. All right, so we multiply the tops together, and we get 4 plus 3i. Now we multiply the bottoms together. Now remember, it is the difference of squares pattern. So we know that those middle terms are going to cancel. So we get 4 times 4, which gives me 16. 4 times 3i is going to give me plus 12i. 4 times, so first outer, inner, so negative 12i. And then negative 3i times positive 3i is going to give me minus 9i squared. Again, those middle terms are going to cancel because it is the difference of squares, and we get 16 minus 9. We see the I squared, so we plug in -1. All right, so now we get 16 plus 9, which is 25, and so our answer is 4 plus 3i all over 25. Now, to put that in a plus bi form, we want the real part separate and the imaginary part separate. So we'd split it up. 4 over 25 plus 3i over 25. So it's a plus bi form. Okay, so this was just a basic introduction. And it was a pretty short video. So I'm going to ask you, if there was anything you didn't understand, to go back and rewatch it from here, okay? All right, we're going to be practicing and talking more about this tomorrow in class. Have a great night.